Imagine you are reading a sentence word by word, and you want to know if it follows the grammar of English. A shift-reduce parser does the same for programming languages. It reads tokens the words from left to right the shift part, and whenever a group of tokens matches a rule of the grammar, it replaces that group with the rule's left-hand side the reduce part. This bottom-up approach is necessary because many languages have constructs that can only be recognized after you have seen their whole right-hand side like a closing brace. A pure top-down parser would get stuck or need backtracking, while shift-reduce parsers handle these cases efficiently and in a single pass. A shift-reduce parser looks like a person with two hands. One hand holds a stack of symbols that have already been processed, and the other hand reads the next input token. The stack initially contains a special start symbol. The two basic operations are: shift, push the next input token onto the stack and move the input pointer forward. Reduce, look at the top few symbols on the stack. If they match the right side of a grammar production, for example E goes to E plus T, pop those symbols and push the left side, for example E back. The parser repeats these steps until the stack contains only the start symbol and the input is exhausted. The stack is like a pile of Lego bricks that you constantly replace with bigger bricks when they fit a known pattern. Explanation: to decide when to shift and when to reduce, the parser first builds a set of LR0 items. An LR0 item is a production with a dot showing how much of the right-hand side we have already seen. For example, for the rule E produces E plus T, we get items. Dot E plus T, nothing seen yet. E dot plus T, E has been seen. E plus dot T, E plus has been seen. E plus T dot, the whole right side is seen, ready to reduce. Starting from the item with the dot at the beginning of the augmented start rule, we repeatedly apply the closure operation. If the dot is before a non-terminal x, we add all productions of x with dot at their start. Collecting all reachable item sets yields the canonical collection, each set representing a possible parser state. Mathematically, closure of I equals I union the set of A produces dot alpha such that B produces dot beta is in I and B equals A. The collection is a graph where edges are labeled by grammar symbols, showing how the dot moves when a token is read. From the canonical collection, we create two tables. Action table, indexed by state and next input token, tells the parser to shift to a new state, reduce by a rule except when the start symbol is completed, or error if nothing applies. Go-to table, indexed by state and a non-terminal, tells where to go after a reduction. For each state S and terminal A, if there is an item A produces alpha dot a beta in S, set action of S and a to shift to the state reached by the edge labeled A. If there is an item A produces alpha dot in S, with the dot at the end and A is not S prime, set action of S and a to reduce by a produces alpha for every terminal A or dollar for end of input. If the item is S prime produces S dot, set action of S and dollar to accept. Go-to of S and A is state T where the edge from S labeled a leads. The tables look like a spreadsheet that the parser consults at each step. Sometimes the tables give two possible actions for the same cell, a conflict. A shift/reduce conflict occurs when the parser could either shift the next token or reduce the current stack symbols. Think of a crossroads where you can either go straight shift or turn left reduce. A reduce/reduce conflict appears when two different reductions are possible at the same time, like being told to choose between two different ways to wrap a gift. Conflicts happen because the grammar is ambiguous or because the parser's look ahead is insufficient. Detecting them means scanning the action table. If a cell already has an entry and we try to add another, we report the conflict. The parser generator then warns the programmer to rewrite the grammar or add precedence rules. A common way to resolve shift/reduce conflicts without redesigning the whole grammar is to give the parser extra knowledge about operator precedence, which operator binds tighter and associativity, whether an operator groups left to right or right to left. For example, star has higher precedence than plus, and plus is left associative. The parser generator records a numeric precedence level for each token and a direction for each operator. When a conflict occurs, the rule with the higher precedence wins. If they have the same precedence, the associativity decides. Left associative prefers reduce, right associative prefers shift, and non-associative reports an error. In our Lego analogy, precedence tells the builder which bricks should be glued first, tighter, and associativity tells which direction to extend the structure when two bricks fit the same spot. Different LR families trade off power against table size. SLR1 uses the simple LR0 items and follow sets for look ahead. It is fast to build and tables are small, but many practical grammars cause conflicts. LR1 augments each item with a single look-ahead token, yielding far fewer conflicts. The tables are huge because every state carries many look-ahead symbols. LALR1, look-ahead LR, merges states that have identical LR0 cores but possibly different look-ahead sets. It keeps the table size close to SLR while preserving most of LR1's power. Most real-world parser generators Yak Bison use LALR1 because it is a good compromise. Enough expressive power for most programming languages and manageable memory usage. The trade-off is similar to choosing a map. A world-scale map LR1 shows every detail but is heavy to carry. A city map SLR is light but may miss small streets. A regional map LALR balances detail and portability. Yak and its open-source cousin Bison turn a grammar description into C code for a shift-reduce parser automatically. $expr plus term brace $$ equals $1 plus $3 semicolon. New line pipe term brace $$ equals $1 semicolon new line semicolon. The tool computes the LR0 or LALR1 automaton, builds the action /go to tables, and emits a function yparse that drives the parsing loop. Read a token, look up action, perform shift or reduce, and call the semantic actions the code inside braces when a reduction occurs. The generated code also contains error handling hooks error. Using Yak Bison saves the programmer from manually constructing tables, handling conflicts, or writing the stack machinery. The tool does all the heavy lifting while you focus on the grammar and the actions. The workflow is similar to using a recipe app. You input ingredients grammar, and the app outputs a cooking plan parser that tells you step by step what to do. Explanation : when the parser meets a token that does not match any action entry comma, it reports a syntax error. Instead of stopping immediately comma, many parsers try to recover, so they can continue and find more errors. Common strategies include : panic mode : discard input tokens until a synchronizing token like semicolon or right brace is found, then resume parsing. Phrase level recovery : insert a missing token, delete an unexpected token, or replace one token with another comma based on a set of repair rules. Error productions: add special grammar rules that match common mistakes, for example, stmt: error semicolon, comma, allowing the parser to treat the error as a valid fragment, and continue. Think of a teacher correcting a student's essay: if the student writes an unreadable word, the teacher may skip it, panic, or guess the intended word repair and keep grading the rest. Good error recovery helps the compiler report many useful messages in one run. In the parser's data structures, the error token error is treated like any other symbol, and the action table contains entries that shift to a special error state, after which the recovery routine runs. Explanation: let us parse the expression 3 plus 4 times 5 using an LR0/LALR1 parser for the grammar. E goes to E plus T or T goes to T times F or F goes to open parenthesis E close parenthesis or id. Step 1: initialize :stack equals open bracket 0 close bracket, look ahead equals id 3. Step 2: shift id: push state 5 from action 0, id equals shift 5. Stack equals open bracket 0, id 5 close bracket. Step 3: reduce f arrow id: pop id and state 5, push f and go to 0, f equals 3. Stack equals open bracket 0, f 3 close bracket. Step 4: reduce t arrow f: use go to 3, t equals 4. Stack equals open bracket 0, t 4 close bracket. Step 5: shift plus : action 4, plus equals shift 6. Stack equals open bracket 0, t 4 plus 6 close bracket. Step 6: shift id 4 : action 6, id equals shift 5. Stack equals ellipsis plus 6 id 5. Step 7, reduce F arrow id, push F state 3. Stack equals ellipsis plus 6 F3. Step 8, shift star colon action 3 comma star equals shift 7. Stack equals ellipsis plus 6 F3 star 7. Step 9, shift id 5 colon action 7 comma id equals shift 5. Stack equals ellipsis star 7 id 5. Step 10, reduce F arrow id, push F state 3. Step 11, reduce T arrow T star F because we have T state 4, star, F state 3, and the item T arrow T star dot F. After reduction, we go to 4 comma T equals 4. Stack now has T representing 4 times 5. Step 12, reduce E arrow E plus T using the remaining E state 0 plus T state 4. Finally, stack contains start symbol E and action 0 comma dollar equals accept. During each step, the parser consulted the action and go-to tables. Reductions correspond to applying the grammar rules, building a parse tree bottom-up. The final tree reflects the precedence of star over plus because the multiplication was reduced before the addition. This example shows how the parser automatically discovers the correct grouping without any extra code. The grammar and the tables do all the work.